All right, you made it to the last video on enthalpy, and this is bonds broken minus bonds formed. So we've learned 4 out of the 5 ways. Calorimetry, you're looking for the word calorimeter to different temperatures, specific heat values. Stoichiometry is kind of the last case scenario if it's not the others, but usually they give you moles or grams of one of the reactants or products and a delta H reaction. Products minus reactants, you're looking for the heat of formations given, or they say refer to the table or go to the back of your book. Hess's law, you're looking for one overall reaction and then steps of that reaction that maybe can be flipped or doubled to add up to the one main reaction. And today we're going to learn bonds broken minus bonds formed, and the easiest way to remember this is you're looking for the word bond. They're going to say bond somewhere. Usually there's a table of bond energies, but as at the very least it's going to have the word bond in the question. Okay, a couple key ideas and then we'll look at an example. When you have a chemical bond, you have to put in energy to break that bond. Picture Red Rover. When you played Red Rover, as a kid, you held hands and it took energy to break that connection, right? You always picked on the scrawniest kid to run, hoping they wouldn't have enough energy to break the connection with whoever you were holding hands with. Okay, putting in energy to break the Red Rover, to break the bonds, that's endothermic. When you make new bonds, we release energy. That's exothermic. So breaking old bonds, endothermic, put in energy. When you make new bonds, formation of new chemical from those bonds, that's a release of energy and it's exothermic. And so to find the delta H of reaction, if we add up the energy required to break the old bonds, which is going to be positive, endothermic, plus the energy released when we form new bonds, which is negative, we are going to, minus, well, it's plus the negative, right? So minus the bonds formed energy, we will get our delta H of reaction, right? So plus the sum of the energies, but it's going to be negative. So plus and negative is negative. Should I say that one more time? You'll get it. If I confuse you, just talk to me. I'll help you out. The one warning is to be careful, because when you look at a reaction, normally we're used to doing products minus reactants. That's the heat of formation, the big mama equation. But bonds broken, those are our reactants, minus the products are the bonds formed. So hopefully I do a better job than the last slide, and let's just do an example, and then maybe you're not as confused as you were when I just talked on that last slide. So using bond energies, I see that word bond, so I know it's a bonds broken minus bonds formed. Calculate the change in energy that accompanies the following, and it's H2 plus F2 makes 2HF. I drew Lewis dot structures for you. I will try to give them to you this unit. We will learn or review how to draw these Lewis dot structures later on. It's a typical AP question, though, to make you draw the structures and then figure out bonds broken and bonds formed. But for this unit, since we haven't reviewed Lewis structures and it's been a while for you seniors, we will give you the drawings. But just know eventually you'll learn how to do these on your own. Okay. Notice that they've given me a nice fancy chart with the type of bond, so a single H to H bond, a single F to F bond, and a single H to F bond, and the energy in that bond. So what this is telling me, 432 kilojoules per mole, that's how much energy currently is being held in that bond. So that could be energy I have to put in to break it. Could be energy like if we're forming a bond, how much energy is released when we form it. That's the energy. So bond energies will always be positive because it's associated with when the bond exists, how much energy is it containing. So now all we're going to do is bonds broken minus bonds formed. So if you notice, let's do like this guy. If you notice, we have to break this HH bond, and we have to break this F to F bond. So here's my bonds broken on this side. We take one of the HH bond energies plus one of the FF bond energies. So that's my bonds broken. Now let's look at the bonds formed. We're going to form this HF bond, and if you look, there's 2 of those molecules, so 2 times the energy to form the HF bond. So bonds broken minus bonds formed. When we math that out, we get a heat of reaction at negative 544 kilojoules, which tells me this is exothermic. And I know there's a release when we form bonds. So this tells me that there was more energy released when we formed the bonds than it took to break. the bonds. Here's a nice question from an old AP exam. So we have nitrogen, diatomic nitrogen. It actually has a triple bond. Again, you don't need to remember how to draw that structure. I'm helping you guys out. There's 3 F2 molecules, so I put 3 of those, and we produce 2 NF3 molecules. So I got all those Lewis structures. Again, don't worry about the dots. We care more about the bonds. Those are the lines between the atoms. And they're telling me that the energy for this reaction, they're giving it to me this time. It is negative 246 kilojoules per mole. So let's predict. It's exothermic. What is bigger in magnitude, breaking or making? Well, if we're negative, it's going to be the making. We are releasing more energy when we make the new bonds than it took to break the bonds that are already there. So that's our little prediction. So before we get into bonds minus bonds, letter C we can do at this point, so I'm not going to skip it. It says calculate the delta H if only 0.256 moles of NF3 is formed, and it's at standard conditions. So this is a stoichiometry. How do I know? Well, they gave me a mole value of a product, and I have that delta H of the whole reaction. And truthfully, like, you might have sat there for a second being like, how do I solve this? That feeling of I don't even know where to start. Chances are it's a stoichiometry one. So I know that for this reaction, we are producing 2 moles of NF3 for every 264 kilojoules that's released, or negative 264 kilojoules. So I just take what's given, 0.256 moles of NF3, 2 moles will give me this energy, so we just do a little math. I get negative 33.79 kilojoules released. Again, that's not going to really help us with this bonds minus bonds. It's just a different type of problem, so I figured you could use the the refresher. Letter D says, oh, well, let me read this part. The enthalpy change in a chemical reaction is the difference between energy absorbed in the breaking of bonds in the reactants and the energy released by the products. That's nice. They told you what to do. So letter D says, how many bonds are formed when 2 molecules in NF3 are produced? So this was getting kids to draw the Lewis structures so they could see. Again, I drew it for you guys, so I just put 2 of those NF3 molecules, and I can see 1, 2, 3, 4, 5, 6 bonds are formed. Letter E says use both the information in the box above and the table of average bond enthalpies below to calculate the enthalpy of the FF bond. So that's a question for us. So we don't actually know the energy that's going to be necessary to break these. We don't know that. That's a question mark. But they've given me everything else. I can still solve this because I have the delta H of reaction that was given to me. So I plug that in, negative 264, and now we do the same process. Bonds broken minus bonds formed. So I know that we're breaking 1 triple bond for nitrogen, and they give me the energy of that triple bond, 946 kilojoules. So there's 1 of those, plus 3 times... Oh no, this didn't get fixed. Ugh. Hold on. I need you to bear with me. This is my x. Plus 3 times x. And this was 272. That's a ripper. Okay, so I apologize for the typo. I fixed it on one version, but apparently not this version that you guys are looking at. So we have 1 times the triple bond of nitrogen, plus 3, we're breaking those F bonds, and that's my question mark. So it really should say 3 times X, minus, now we're going to do the bonds formed. We said in part D we are forming 6 of the N to F bonds. So 6 times, and we have that value, 272. Okay, so sorry about that confusion. That was just my bad. I misread it the first time. Now we can math. So when I take 946 plus 3x, oh, I just fixed it on this slide. That's why. Okay, so it's fixed on this slide. So if the last slide confused you, just look at this one. So 1 times 946 plus 3 times the x, we're looking for that value of the FF bond, minus 6 times 272, which is 1,632. So I get the average bond enthalpy of the FF as 140.7. And that's kilojoules per mole. That should always be positive, because when we're talking about bond energy, I'm talking about the energy associated within that bond. So hopefully this helped. We'll do tons of practice on these problems in class tomorrow.